Welcome to the part 3 of our series of videos of 9th class mathematics. In our previous two videos, we have been discussing about various kinds of numbers like natural numbers, whole numbers, integers, and we have discussed a lot about rational numbers. So rational numbers are those that can be written in the form of p by q, where p and q are integers and q not equal to 0. Likewise, we have defined rational numbers and saw a few examples about rational numbers. Also, we have discussed about converting the rational numbers, those are not integers, into decimal forms, and there we have encountered two kinds of decimal forms. One is terminating decimal form and the other one is non-terminating recurring decimal form. Also, we have plotted a few rational numbers on number line. Right, in this video we are going to discuss a wonderful topic, actually the topic that begins in our 9th class. So stay focused and learn carefully. Right, okay, here, yes, we can write rational numbers in the form of p by q, or we can define those can be put in the form of p by q are called rational numbers. Now this insists me or this makes me to think, are there any numbers those can't be written in the form of p by q form, those can't be expressed in p by q form, where p and q are integers and q not equal to 0? Are there any such numbers those can't be written in the form of p by q? Keep it in your mind. And second one, okay, while we were discussing about converting the rational number into decimal forms, as I said earlier, we have encountered two forms. One is terminating decimal form, the other one is non-terminating repeating decimal form. Now these two again ask me, are there any numbers those who have non-terminating non-recurring decimal form? This is the third one of our categories. Non-terminating non-recurring categories, in the sense terminating, first one, second one non-terminating recurring, and the third one non-terminating non-recurring. Are there any such numbers? We have not discussed about these things. And third one, this makes me interesting. Third one, suppose we have filled the number line with all the available rational numbers. Of course, rational numbers is a huge list. It has no ends, no boundaries. But however, think that we have filled the number line with all the rational numbers. Right? Even though there are some gaps appeared on the number line. This is interesting. Since we have gaps on the number line, it implies that there are some numbers beyond rational numbers, other than rational numbers. So gaps on the number line, even all the rational numbers are filled. And one more instance that has been given in our textbook, you see here, we have three equations written here. One is x square is equal to 4, and the other one is 3x is equal to 4, and third one is x square is equal to 2. So what do you mean by x square is equal to 4? Okay, x is equal to square root of 4, therefore x is equal to plus 2 or minus 2. By squaring which number we get 4? Either 2 or minus 2. Whatever you square you get 4. That's why x is equal to plus 2 or minus 2. If I ask you to represent these numbers on number line, yes, it's easy. It's very easy to represent them. Okay, come to the second equation. 3x is equal to 4 and x is equal to 4 by 3. Okay, bring this 3 to this side. Again, if I ask you to show this 4 by 3 on number line, why not? You are ready to show it. 0, 1 by 3, 2 by 3, 3 by 3 next one, that means 1, and then 4 by 3. Here it is, you show. Right, come to the third one. X square is equal to 2, then x is equal to square root of 2. So what is the value of square root of 2? you may have little knowledge about these square roots, right? It is not a perfect square, you know. Some perfect square are there. Some, see, root 1 is equal to 1, root 2, okay, keep it aside. Root 3, keep it aside. Root 4 is equal to 2, because 2 2s are 4. Again, root 9 is equal to 3. Root 16 is equal to 4. You know, you may have little knowledge about all these things. Because why square root of 9 is equal to 3? Because we have 3 3s are 9. But we have anything, same things will give you, same multiply the same things and give you 2. We don't have such integer. We do not have such integer. That's why, what is the value of square root of 2? Anyway, we are going to find it. But for the time's sake, I'm going to tell you the value of square root of 2 is 1.4142135, and it keeps coming. It keeps coming. Yes, we're going to find it. Anyway, so if you notice that it is of the form, it is neither terminating, you never get 0 in the division, and in fact it does not show any pattern or rhythm or repetitive nature, even though you go millions and trillions of the places after the decimal. Yes, they found so many places after the point for the square root of 2. So let me name it. It is a non-terminating, non-recurring decimal form. That's what we have asked in our second question at the beginning. Yes, there are some numbers, those who have non-terminating, with non-recurring nature, like square root of 2, square root of 3, square root of 5, square root of 6. All these, they, if you start finding them, start finding the values of those numbers, strictly speaking, the non-perfect squares, the value of non-perfect squares under root, you will get a kind of decimal form that neither terminates nor repeats. So all these things probe me, or all these things pulls me to find a new world of numbers. That is what we are going to discuss. Irrational numbers. So until now we have discussed about rational numbers. Yes, we have a good knowledge about rational numbers. They are represented by Q, and now we are entering into the world of irrational numbers. This is the new one that has been introduced in our 9th class, irrational numbers, in detail, in fact. What are irrational numbers? Okay, obviously we are going to represent irrational numbers by either Q dash or S. Okay, right. But these irrational numbers are different from rational numbers. They do not mingle with rational numbers, right? They have a separate world. That's why, what are irrational numbers? Oh, okay, irrational numbers are those not rational numbers are called irrational numbers. That's it, definition over. But to be specific, or to be exact, irrational numbers are those numbers which cannot be written in the form of P by Q, where P, Q are integers and Q not equal to 0. Those cannot be expressed in the form of P by Q. Yes, there are such numbers, those can't be written in the form of P by Q. That's what we have seen now. Non-terminating, non-recurring. So had it been terminating, or had it been non-terminating recurring, it would have kept in P by Q form. Since it is neither terminating nor repeating, we cannot write it in the form of P by Q. So yes, we have the existence of such numbers in our number system. And second one, right, these irrational numbers are going to fill the gaps of on the number line, and thus completes the number line. So these rational numbers and irrational numbers together called real numbers. That's what our title of the chapter, real numbers. Or, okay, right, real numbers. Let us respect or, let's keep capital letter or, real numbers. So real numbers is the combination of rational numbers and irrational numbers. Remember, both are separate. We cannot separate natural numbers, whole numbers, integers from rational numbers, but irrational numbers can't be clubbed with rational numbers. That's why, see, if I write n like this, w like this, z like this, and then if I write q like this, So Q has all the things inside it. It has natural numbers, whole numbers, integers. You can understand this picture. And this Q dash is distinct from this, different from this. And these together the combination of these rational numbers and irrational numbers together called real numbers. That's what our chapter is. Right. So keep all these things in your mind. What is an irrational number? Yes, tell like this. Those can't be put in the form of P by Q are called irrational numbers. An example. Okay, write like this: 1.324671 1, 2, 4, 5, like this. Write randomly without any repetitive nature and put some dots to show that it is non-terminating. It becomes an irrational number. To be more precise, you can give the examples of square root of 2, square root of 3, square root of 5. You should not give square root of 4, okay, because it has 2. It is a rational number. So you can give these non-perfect squares. So let me show that if n is a perfect square, then root n becomes rational number, right? If n is a perfect square, root n becomes rational number. Perfect square in the sense, if I take root 16, square root of 16, it is 4, then it is a rational number. If n is not a perfect square, then square root of n is irrational. In the sense, root 5 is not a perfect square, so it is an irrational number. So give examples for irrational numbers like square root of 2, square root of 3, square root of 5, square root of 6. Likewise, you can keep on giving. Right? This is all about irrational numbers, introduction of irrational numbers. And now you can see, okay, we're going to find value of square root of 2, square root of 3, and if time permits, square root of 5, and so on. See here, they are denoted by S or Q dash, irrational numbers. So which can be expressed in P by Q form or rational numbers. Read the textbook. That's why I'm showing you in the textbook. So these type of numbers are called irrational numbers. Read what are irrational numbers like this. These irrational numbers, and they can't be expressed in the form of P by Q. That's what. And if we go for a bit history, see, these irrational numbers are supposed to be found in 5th century BC. My God, 5th century before Christ. By Pythagorean in Greece. Pythagoras followers are known as Pythagoreans. So Pythagoras is the imagine that he's a captain of the group, and they have a school, they have a place where all these researches are carried out, and they found first time about these non-rational numbers, which were not rationals. They found which were not rationals. They called irrational numbers. So the Pythagoreans proved root 2 is an irrational number, and later in these theories of Syrian showed that all these are irrational numbers. Right, we have also our Indian contribution. We have in Syllabus Sutras, we have the reference of irrational numbers. Right, read them once or twice so that you can remember them. So this is all about the introduction of irrational numbers. Now, okay, as I told you, let's try to find the value of square root of 2 by a process known as long division method. Let's try to find it out to confirm you that it has non-terminating, non-recurring decimal form. So this is the way we are going to do value of square root of 2. See, keep 2.0000000000 like that. Take as many zeros, as many pairs of zeros you can, and pair them like this, and draw a line like this. Draw a line, big line downwards. Right. Now we start with 1 ones are 1. Okay, because anyway 2 2s are 4. Take Q beyond 2. So 1 ones are 1. So subtract 1 from 2, you get 1. Since we are crossing decimal point, put point here and drop down 2 zeros. This is what we are going to do. This is the mechanism you need to understand. There is a little about this kind of things in 8th class, but however 8th class is not that much done properly. That's why listen carefully. Now we double this digit. We keep here 2, and here we have to write the same number. Suppose if I write 1 here, I write 1 here, and I multiply with 1, 21's 21 I had to write here. But it is far less than 100. That's why I want to That's why I want to, okay, wait a minute, let me erase my pen. Okay, 0 0. So that's why I want to keep here a number closer to 100. So if I write 4 and 4 here, I multiply with 4, 4 24s 96, and now 100 minus 96, 4, we know that. Now this is first layer, imagine that is first layer. Now what we are going to do is we double this digit and we write 28 here, or you can simply add these two, 28. And again you have to keep, we are entering into second layer. Again we have to keep here and here same number and drop down 2 zeros, don't forget. So if I write 1 here, if I write 1 here, I had to multiply with 1, 1 281s 281. Okay, 2 will give you the number more than 400, that's why 1 is enough. So if I subtract 400 minus 281, 119 I'll get. Again bring down 2 zeros and double the digit or add these two. So this is second layer and we are entering into third layer, 282. Again keep a number here and here that suits 11,900. I am going to keep 4 anyway. So if I multiply with 4, I'll get 6 9 112, 11,296. And again if you subtract this, 40604, again drop down 2 zeros and actually you have multiplied with 4, so 2828. So here and here we have to keep same number. Perhaps 2 will be enough for this. So 282 is 56,564, right? Again subtract, you will get 6 3 8 3, and again drop down 2 zeros. So with what we multiplied 2 and 28284, and here you have to keep same number. So you can see that 1 will be enough for that. 2 takes you more than the number. So likewise we carry this process. So as long as we proceed, we never get 0 anyway in as the reminder. So it never stops. And moreover, the interesting thing is there is no specific pattern and they come randomly like this. That's why it is known as non-terminating non-recurring decimal form. If it is a non-terminating recurring decimal form, we would have kept it in the form of p by q. So that's why we cannot write this form in the form of p by q. That's why square root of 2 is categorized under irrational numbers. Right? Do you understand the process? Try on your own. Okay, I'll help you to do root 3 also, square root of 3. So that remind you have roots, you have to find square root of 5, value of square root of 5, value of square root of 7 likewise. So let me find out for your convenience square root of 3 by long division method. Right? Shall we start in the same manner? Why not? Take 3.0000000000 like this and bring down a big line. Use your roller to make it beautiful. Now again we have to start pair. Don't forget to pair these zeros. You can take any number of pairs. Now here I have to put 1 ones are 1 again, 2, drop down 2 zeros, put decimal point, double the quotient. So here and here I have to put same number. I want to put something like 7. Check for the other numbers, they all not sufficient here. So 7 27s will give you 189, 140, okay, and subtract 11. Again drop down, bring down 2 zeros. Okay, we have multiplied with 7 anyway. So come to the second layer, it is 34, right? 27 plus 4, 34. And again here and here we keep same number. 343 is 1029, right? Good. So subtract 71, isn't it? 1100 minus 1029, 7100. One more pair brought down, and again with what we multiplied 3, that's why it becomes 346. Right, again we have to keep same number. Okay, 2, I think 2 will work. 2362 is 6924. Good. Subtract 176, 6, 7, 176. Bring down 2 zeros again, proceed further. Okay, with what we multiplied 2, so 3, 4, 6, 4, and here we need to keep the same number. Whatever number you keep, you observe that it is 34,000, it is 17,000 only. So that doesn't work. Keep any number, it doesn't work. That's why we keep 0. Okay, this kind of situation you must understand. 0, and so something like 0, and again we bring the same number downwards, and one more pair we bring down. We have done nothing, zeros, that's why I add these two. So 3, 4, 6, 4, 0 again, and again you have to keep a number here and here. So that is 5. Notice that 5. So 5, this multiply 5 with this number and you will get 1732025. 1732025. So if we subtract, we have 27,975, and again we bring down 0, 0, and we make this 3, 4, 6, 4, 1, 0. Again, if we keep a number here and here, that will take you beyond the number. That will take you beyond the number anyway. Okay, so we keep 0 again, and likewise we proceed. And you will get some digits like that. So here also you observe that square root of 3 is also a kind of number that have non-terminating, non-recurring decimal form. Had it been a terminating decimal, it would have been a rational number. Since it is not having that nature, it is an irrational number. So all these numbers, observe here a box, square root of 1 rational number, square root of 2 irrational, square root of 3 irrational, square root of 4 rational, because we have answer perfect square, it is an integer. So 5 irrational, 6 irrational, 7 irrational, 8 irrational, 9 integer. I think you understood well. Now we're going to show, okay, we have done one task, that is found the value of root 2, root 3, and you can do the rest, and prove that they are categorized under irrational numbers. And now we are going to fill the gaps with irrational numbers, as I told you earlier. Let us try to represent some of the irrational numbers on the number line, and to show that they can be plotted on number line even though they do not have any specific form. Right, don't think that square root 2 is something a demon like number. Okay, it is something like 1.4, 1.414 nearly, and so on, of course. So it is a number nearly closer to 1.5, 1.5. Similarly, square root of 3 is something like 1.73, 2, closer to just beyond the 1.5. Likewise, we need to understand about irrational numbers. Don't think that they are something different. Okay, so the combination of rational numbers and irrational numbers is called real numbers. Our boss, our world of numbers now, real numbers. That's why once we fill irrational numbers on the irrational numbers also on the number line, then the number line can be called a real number line. Right? Let's keep moving. Now let us try to show or represent square root of 2 on number line. Let us represent square root of 2 on number line. Right. So for this we take number line as usual, 0 like this, 0, 1, 2, minus 1, minus 2. You can draw like that. And here we're going to, in this portion, we're going to draw a square of unit length, 1 unit length. Anyway, this is 1 unit length. That's why I'm going to draw a square like this. Yes, you know the square. All its sides are equal in length. Now, what I'm going to do is, I'm going to draw one of its diagonals. Anyway, you know square like this, 1, 1, 1, 1, our square. So the length of the diagonal can be found out by finding like this, see, square root of 1 square plus 1 square, because its side is of length 1. So square root of 1 plus 1, square root of 2. So in that manner, this becomes square root of 2. So this dotted line, the length of this dotted line represents as root 2 units. So that's what the length of square root of 2. So I wanted to bring it down to the number line. So for that, I'll take circular, circular, we draw circles, that one. Circular, and this particular 0 as center, and extend it legs, one of its leg to this point, and draw an arc like this. Yes, there it is. And that point shows you the spot of the square root of 2. So don't think that square root of 2 is some different number or something like devil-like number, and that is never going to mingle with rational numbers. It has value. It has value very much closer to 1.5, 1.5. What I mean is 1.5. It is very close to 1.5. To be specific, it lies between 1.4 and 1.5. So it has location. So to show it precisely on the number line, we use this method. Okay. So this is the spot of square root of 2, very much close to 1.5. In such a manner, we represent other numbers also. For instance, if you want to see root 3 on number line, yes, start again in the same manner. First we show root 2. First we pick root 2 as we picked in the previous topic. See, again I'm going to draw a perpendicular line here, okay, of 1 unit length only, same length, same this length. Now I'm going to join like this. Yes, now I can find a right angle triangle. I can find a right angle triangle like this, with base square root of 2 units, and one of its side is 1. Now almost similar to the pattern that we have done. There we used square. Here I am just confining to right angle triangle only. So how can I find this length? Simple, same, square root of 2 square plus 1 square under square root. So square root of 2 plus 1. Square root of 2 square is 2. Normal 2, you will get 4. But anyway, here we have square root of 2. So obviously we get square root of 3. So the second dotted line, this dotted line shows me the length of square root of 3. This much longer is square root of 3. Again I bring it down to the number line by using that circular, by drawing the arc of the same length. So here this point shows me root 3, square root of 3. Again, don't think that root 3 is a distinct number, but here it has 1.732 like that value. So it is almost 1.7. Okay, 1.7. Nearly 1.732 like that we can show. So this is the way we represent irrational numbers on number line. We can show root 5, we can show root 6. So if we keep on continuing like this, again if you draw a perpendicular line of 1 unit length here at this point and join these two, and you will get root 4, and again if you draw a perpendicular line here and join this, you will get root 5, and thus you can continue. Again if you draw a perpendicular line, you join this, you can get root 6. You can continue on the same lines, or in some specific cases we can do like this also. See here, see a specific case, a particular case. See here what I have done. Yes, I have drawn a 1 unit of length here perpendicularly at 2. So this is 2 units length, and this is 1 unit length. And if I join this, what happens? This length is square root of 2 square, this one, plus square root of 1 square of this number in fact, and 1 square. So you will get 4 plus 1, and that is root 5. So this dotted line represents me of length root 5 units. So if we draw an arc like this, and this particular point shows me the position of square root of 5. Okay, so 2 units, 1 unit, 2 units, 1 unit gives us what? Square root of 5. Okay, square root of 5. Likewise we can keep on finding things like spotting rational numbers, spotting specific numbers directly, and some numbers we have to follow the previous method. See here, I'll show you a beautiful structure what we are speaking. See here, likewise, if you keep on drawing perpendicular lines of 1 unit length at the end of the diagonal, I should say, so you will end up with like this: square root of 2, square root of 3. What do you mean by square root of 2, square root of 3? Yes, this length is square root of 2. We bring it down to the number line. This is square root of 3, and this one root square root of 4. Mind you, this is not an irrational number, it is equal to 2. So this arc cuts at 2 here, and again root 5, root 6, root 7, like that we can finish this, and you can continue and you'll get a beautiful picture popularly known as square root spiral. In page number 10, we have a question under the heading think, discuss and write. Here Kriti said root 2 can be written in the form of root 2 by 1. So it is in the form of p by q. That's why it is a rational number. She's thinking like that. Do we agree with this argument? But before actually defining the rational numbers, we must understand something carefully. That is, yes, all those that can be put in the form of p by q are rational numbers, provided p and q are integers. They must be integers. So numerator must be an integer and denominator must be an integer. However, q not equal to 0 anyway. So you must take an integer here, an integer here. But what did she do? See, square root of 2 is equal to, she wrote square root of 2 by 1. Here she took other than integer. That is an irrational number in fact. So it is not a valid expression, because root 2 is anyway not an integer. That's why even though it looks as if in the p by q form, it is not a rational number, it is an irrational number. That's it. And see, at the end of the page you find the value of square root of 3 up to 6 decimals. We already found it. Please verify it. Now see, in between you have know about pi. There is a number called pi, not choco pi in fact. It is also an irrational number. Anyway, we will discuss it later. See here, the value of pi is this much longer and it continues, and that's pi value roughly we take 3.14, and it looks as if 14th March month, 3rd month anyway. So that's why it is also the birthday of Albert Einstein, March 14th, 1879. That's why it is known as Pi Day. Pi Day. What is the Pi Day? March 14. Why? March 14, why? Because value of pi is 3.14. Okay, 3 March 14 date. And besides, we have a special day, that is the famous scientist Albert Einstein's birthday. Okay, all these are history, you know it. Right, now let's quickly jump to exercise 1.2, a small exercise, so focus on it. Okay, let's go for exercise 1.2. Classify the following numbers as rational or irrational. So what about square root of 27? It is not a perfect square, that's why it is irrational number. Okay, irrational number. There are only two categories until now, rational or irrational. That's what we are segregating all these things. What is second one? Square root of 441. Okay, it is a perfect square, 21. That's why it is rational. And what about third one? Third one, see, notice the number 30.2323. Okay, until then okay, but 42345. It looks as if some disorder. Nothing is repeating and non-terminating. So that's why it is irrational. Third one is irrational. And what about fourth one? 7.484848. Okay, it is it looks as if non-terminating repeating decimal. That's why it comes under the category of rational number, because we can write it in the form of p by q. And what about fifth one? 11.2132435465. Stopped. Notice that it is stopped, terminated. So whatever that terminated is nothing but rational. because it can be easily converted into P by Q form. And sixth one, the last one in the first one, 0.303003000, likewise. It's not a rhythmic repetition, somewhat repeating but not properly repeating. Also looks as if it is non-terminating. So non-terminating, non-repeating, that's why it comes under irrational numbers. So likewise we can discriminate or classify the numbers into these categories. Let's go for second question. Explain with an example how irrational numbers differ from rational numbers. Right, again you can write rational numbers or something like Q. You write Q here and Q dash here. These are the numbers. Those can be put in the form of, those can be written in the form of P by Q. In the form P by Q, where P, Q are integers and Q not equal to 0. And what about irrational numbers? Those cannot be written in the form of, those can't be written in P by Q form. So you can differentiate like that. You can show the difference like that. And give an example. Example for rational numbers is 3 by 7 or root 16, like that you can give. And for irrational numbers you can give an example like root 10 or root 2, or you can write 1.234263 and something that is neither repeating nor recurring form. You can take like that. Right, these are the differences of rational numbers and irrational numbers. Also you can extend it. You can write these rational numbers will have terminating decimal form or non-terminating recurring decimal form, and these irrational numbers will have non-terminating non-recurring decimal form. Likewise you can write one more difference. Now let's quickly jump to question number 3. Find an irrational number between 5 by 7 and 7 by 9. Third question, find an irrational number between 5 by 7 and 7 by 9. Okay, you need to convert them into decimal form to find an easy way. Right, 0.7, yes, 5 divided with 7, 0.7 7s are 49, 1 0, 7 1s are 7, 3 0, 7 4s are 25, 2 0, 7 2s are 14, like that. Anyway, you get 0.71142 and so on. At some point you may get a repetition. You know it is non-terminating. Observe the denominator. We have done a principle. We have obtained a principle to find it whether it's terminating or non-terminating. Second one, 7 by 9. 7 by 9, how to change? Multiply, divide 7 with 9. 9, okay, 9 7s are 63, 7, 9 7s are 63, 7, like that. 0.7777. This is the second one. So first one is 0.7142 and so on. Second one is 0.77 and so on. So in between you can write 0. Something like 7234267, like that. A random form, write down, and it will be the example for a irrational number between 5 by 7 and 7 by 9. You take between 0.71 and 0.77. You can start with 0.72, 0.73 and put as many digits as possible without any proper order. That becomes an irrational number. And again the same case in the fourth question also. Write find two irrational numbers between 0.7 and 0.77. So 0.7 and 0.77. So you treat this as 0.70 and you can write now 0.71238248, like that, and put some dots. And again 0.752368, like that you take. Mind you, it should not be terminated, as well as we should not find any repetition. If we express in such a manner, it can be called an irrational number. Right, fifth one and sixth one do on your own. Find the value of square root of 5, find the value of square root of 7. We have done for square root of 2, square root of 3 in our previous examples. And also try to locate root 10 on number line. You can do it, root 10 on number line. We can take 3 units here and 1 unit here. Okay, let me show you clearly. Take a number line like this. 0, 1, 2, 3 and 4, and take all these as one side, 3 units, and draw 1 unit length here, 1. Join this. Perfect. This will be square root of 3 square plus 1 square, that equal to square root of 9 plus 1, that is root square root of 10. So this diagonal measures up to square root of 10. Take a circular and put your needle here at 0 and extend up to this point and draw an arc, and this place shows square root of 10. Do it properly with the instruments. And find 8th question. Find at least 2 irrational numbers between 2 and 3. Again the same kind of question that we have done in 4th and 3rd. So now find at least 2 irrational numbers between 2 and 3. If these numbers are multiplied, you have taken a couple of numbers, and if you multiply them, and if it is not a perfect square, you get 6, and if it is not a perfect square, and put it under square root, and it is an irrational number between 2 and 3. Yes, clearly this value lies between 2 and 3. So one such number is, and there is a principle like this: if a and b are 2 integers, and if their product is not a perfect square, then square root of ab will be a rational, in fact an irrational number between a and b. Anyway, if it is not a perfect square, it is an irrational number, and moreover it lies between a and b. That's what we need to catch. So likewise, so one number is square root of 2 into 3, that is square root of 6. So you have 2, square root of 6 and 3. And if you want to find one more number, multiply these two again, 2 into root 6, and you keep square root of 2 like this, I mean square root like this. So to make it comfortable for you, I'll write inside that square root of 4, instead of 2 I use square root of 4, both are same, into square root of 6. So square root, big square root, and under that a small square root of 24. So this is another irrational number between 2 and 3. Along with 2 and 3 we have in fact in between 2 and 3 we have root 6 and square root of 24. So for convenience we express like this, we express in this manner. See, square root of 6 means we write 6 to the power of half, and square root of 24 means first find square root of 24, to that value find the square root of 24 square root. So 24 1 by to the power of 1 by 4. ఈ ప్రాబ్లం మళ్ళీ ఒకసారి పెట్టమ్మా దీవెన్. రికార్డింగ్ ఉంటావా? See the 8th question. Find at least 2 irrational numbers between 2 and 3. At least. So we need to find some irrational numbers between 2 and 3. Suppose there are 2 numbers a and b, and if their product is not a perfect square, then square root of ab is an irrational number lying between a and b. In the same lines, if we think, yes, 2 and 3 are 2 numbers given, if we multiply them we get root 6, and since it is not a perfect square, square root of 6 lies between 2 and 3. Square root of 6 is an irrational number between 2 and 3, but asked for 2. So 2 square root of 6, 3. Now to get another one, we multiply any 2 numbers, any pair of numbers here, take 2 and root 6, multiply them and find its square root. Then it is another number between 2 and 3. Actually it is inspecific, it is between 2 and root 6, but anyway it is between 2 and 3. So how do we multiply this? So square root of, make it square root of 4, okay, and this is square root of 6. So this is square root of 24. Yes, we can find double square root. Suppose if I have like this, see, under that first square root 4 and second square root you get 2. So the value of this thing is 2. So in the same manner, if I write in different way, 24 whole power half. So in short, we write 24 whole to the power of 1 by 4. All these you understand better in the latter. So the numbers lying between, in fact the irrational numbers lying between 2 and 3 are, one is square root of 6 and the other one is this one. 24 whole to the power of 1 by 4. What does it mean? You need to find double time square roots. So one is 6 power half, 1 time square root, this one, and second one is 24 whole to the power of 1 by 4. These are the two numbers, in fact irrational numbers, lying between 2 and 3. And you can find one more by using root 6 and 3. Okay, try it on your own. Right, let me quickly jump to question number 9, the last one in this exercise. True or false statements. Let's go on quickly. Every irrational number is a real number. Okay, anyway, definition of real number I should introduce you here itself. So we have learnt about rational numbers and irrational numbers. So these two together called real numbers. This is what the definition. Actually I want to present you in a different way, but here for the context sake I am explaining you. The combination of rational numbers and irrational numbers is called real numbers. I will explain you in the next video, but here for the sake, see, every irrational number is a real number. Yes, true. Every irrational number is a real number. That is true. First statement is true. And second one, every rational number is a real number. No doubt, every rational number is also a real number. Every real number need not be a rational number. Every real number need not be a rational number. Yes, every real number need not be a rational number because it can be rational. Yes, root 2 is a real number but not a rational number. That's why every real number need not be a rational number. It can be rational also. Root 2 is irrational. Root 2 is irrational as well as real. And fourth one, square root of n is not rational if n is a perfect square. If n is a perfect square, like something like root 16, it is not irrational. That means it is rational. Yes, correct. Root n is not irrational. That means root n is rational if n is a perfect square. Done. Okay. And fifth one, root n is irrational if n is not a perfect square. Yes, you all need to understand this syntax and I should say the meaning of implication of the statement. So fourth one and fifth one are true statements. And sixth one, what do you give? Fourth one, example, square root of 16 is a perfect square, hence it is a rational number. Fifth one, square root of 5, since n is not perfect square, it is an irrational. And sixth one, all real numbers are irrational. This is quite a false statement. All real numbers need not be irrational. They can be rational also. We can take one is a real number as well as a rational numbers. All real numbers are irrational. No, all real numbers are both irrational as well as rational. Likewise, we can finish this exercise. Please understand and improve your knowledge, and hope this will help your learning further. Thank you very much. Wait for the next video.